Hello, everyone.
Welcome
Thank
all.
you for attending today's webinar. OIM Analysis version 8.5, a highlight of what's new. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these at the end of the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer via email. A copy of today's slide deck and some links to additional materials are available in the resource list. The widget looks like a green folder. You expand your slide area by clicking on the Maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately one day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce the presenter for today's webinar, Dr. Stuart Ray. Stuart was first introduced to EBSD as an undergraduate student at Brigham Young University, working with the first system in North America. He then moved on to Yale University to pursue a PhD under Professor Brent Adams. His thesis research focused on automating the EBSD technique. This effort led to the first fully automated EBSD scans in the fall of 1991. After graduating, Stuart joined Los Alamos Lab and continued work in microtexture and texture analysis using both the OIM technique and conventional X-ray diffraction. Shortly after TSL was founded, Stuart left Los Alamos and joined the startup company, commercializing the OIM technique, working primarily on software development. He has continued in this role through the purchase of TSL by EDAX. The original OIM system at Yale could index approximately one pattern in 3 seconds. Modern systems have come a long way since those early days, with speeds now exceeding 4,500 index patterns per second. Stuart is closely involved in the continued development of the technique, as well as in working with scientists all over the world in applying the technique to their materials research. Now over to Stuart.
Welcome, everyone. It's good to be with you this morning or this afternoon, depending where you are, or evening. I'm going to focus on today on some of the new features in OIM Analysis, the 8.5 release, and talk about some of the new features that we're excited to put into that release. I'm not going to talk much about the OIM Matrix module, which is for dynamic pattern simulation and dictionary indexing. We talked about that in a previous webinar. And that was the major focus for OIM Analysis 8.5, that in support of Apex, the new Apex software for collecting EBSD data and EDS data. But we're going to talk about some of the other helpful features in this release that haven't got as much attention. So here's actually the list of all the things that in our kind of release notes, and I've highlighted the ones in red that we'll be talking about today. There are a few others, some minor things that I won't be talking about. But as opposed to a lot of text, let's go into some other approaches, the graphics and the fun parts. So if you're like me, ideally I would organize all my scans maybe by material or by the organization I worked with or by a specific project, but the reality is that I just jumble them all together in a mishmash. Sometimes I have a hard time finding that scan I did on copper film in 1990-something. So that can be difficult. And I know a lot of users struggle with that. And so we're introducing, got to have some fancy graphics, a new and improved OIM Data Miner. And it really is a big improvement over what we had before, and I've been using it quite a bit to go through old hard disks and old data that I'm trying to find things. So it looks like this. You'll notice there's a lot more graphics involved in the old version, and I think that really helps you understand what you're looking at when you're looking for a good data set you created once upon a time. So this is the basic a screenshot of the OIM Data Miner. And you'll notice there's a whole new search engine down there in the left, bottom left. The building of the database is quite a bit different. It used to be completely focused on a hard drive, And now you can just enter what folders you want to do. This saves a lot of time in building the database, so it doesn't have to search through folders that you know there's nothing in, system folders, Windows folders, whatever it might be. So you can pick the folders you want to search, and also the types of files that you want to consider. And you'll see there's a lot of different file types that it can handle, and they're all ones associated with the software. So the elements of an entry, so if you look there, I've selected the top row. You can see the bottom right, those thumbnails. You can see larger versions, so you can see what you're looking at. And so these are the elements of an entry. In terms of the graphics, it will always produce an IPF map for data sets, things like OSE files, ANG, HDF, OIM files. It will show an IPF map, an IQ map, and a phase map, if there are multiple phases. And it will also show, it goes through the software now and finds a pattern with a high IQ and a high CI, if there's patterns available in the data set, and shows that pattern as well. The other columns besides the graphical ones are the data set, so it's a name from the file or the name of the data set in the project. It gives the file name, the full path of the file on the disk, the file type, date it was last modified. It will give the number of data sets in a project, if it's an OIM or even an HDF5 file type. It will have a list of all the phases contained in the data set. That's the names used, the symmetries for each one, and it will actually give you quite a bit of information on the phases in terms of the space group, the point group, the Lowry group, depending on what was recorded. We'll show the number of points in the data set, step size, the dimensions, average confidence index. If there's EDS data, it will show which elements were recorded, the counts, the ROIs for each element that was recorded. And it will give the size of the patterns. Now, it's quite a bit different. It can now look for the phase files, so BMT files, or our new OEM file format, which I'll talk about a little bit later. And for those, it won't show an IPF map. The IQ map is replaced with a master pattern if you have the OIM Matrix module installed for dynamic pattern simulation. It will show a little wireframe, ball and stick model for the unit cell, and also an EBSD pattern if available. And you can see the other things. Some of the columns will have data that's not available, and there's just a dash there or a 0. Otherwise, the information is pretty similar. The only difference is points. Instead of it showing the number of points in a data set, it shows the number of atoms in the unit cell. And that's after you've applied the space group symmetry. And the elements are the elements for the atoms. So you can know which elements are in your phase definition file. So just to show you, if you click on an entry, it will show more detailed information down in the bottom right there. And you can actually use it to delete files, or you can open a file. You can open the file location, so you can see it in the Windows browser, or you can open it in OIM Analysis and it will load it, and then you can start up doing your operations and analysis of that data set. Oh, there's the slide that just described what I was trying to say there, sorry. There's also a new search engine down here on the bottom left, so you can search by chemistry in our yes, no, maybe type approach. You can also search on the phases, symmetries, elements, and it's a narrowing or a winnowing filter. So if I go look for all the ones with iron, I might get 828 entries, or I had 828 entries in this database and 36 of them have iron. If I then look for the ones that have austenite associated with them, either in the name, or the data set name, or the file name, that winnows down to 11 entries. If I look for ones with moly in them in the element list, so I can further narrow it down that way, then I get 6. So you can do kinds of little tricks, and and get started. There's one other little trick. You can use a exclamation point. So if you do exclamation point iron, it finds everything that does not have the word iron. Just a little hint there on that dialog box. So double clicking on a BMT or OEM entry will pop up the structure builder, which is a new feature in OIM Analysis 8.5. And so let's talk about that. So the structure builder is basically the way we use to build a phase file or load one or import it, whatever we need to do. So it shows various information like you're probably familiar with. Previously, this was only in the data collection software, whether that's OIMDC, Team, or now Apex. And you'll see the reflector list there. It has a new feature in that you can go through and if you have the dynamic simulation capability installed, then you can load those individually, or you can use that to figure out which are the best reflectors. It also has, you can store now experimental patterns with a structure file. This is nice so that if you have it, for example, in this mineral we have here, I have 3 different patterns that I can then keep around, so I make just for reference. And then you also have the master pattern information for the dynamic pattern simulation. And so the new OEM files can contain all this information, whereas the BMT files only contain the information in the left side of the diagram plus the reflector list. Whereas the OEM files include all the BMT information plus some experimental patterns and their associated pattern center so that you can index them. And as well, the OEM file also includes the master pattern. So the crystal structure group, some new things there. It has a capability of you can set a different level for indexing, the Huff indexing point group, so that if you are working with something with pseudosymmetry and you don't want to deal with that, you can go ahead and set it to a higher symmetry level. The atom positions are needed to generate kinematic structure factors or to calculate dynamic EBSD patterns, so we also have that information. In terms of pseudosymmetry, I wanted to come back to this and just add a few thoughts to it. In my mind, there's really 2 types that we tend to encounter. One is something that mimics one symmetry. An example is 2 stacked cubes, and I'll show you an example. The other more common one is things that are, say, slightly tetragonal or orthorhombic. So you have a stretched cube, for example. The most notable example is martensite, and there the tetragonality is typically 2%, can be a bit more, but typically less than 2%. It's a function of carbon content, which is difficult to measure. But let's go back to this idea of stacked cubes pseudosymmetry. So an example I've worked with is kesterite. It's a tetragonal crystal, and if you look at it, it almost looks like 2 stacked cubes. The difference are the green atoms you see there, which isn't perfectly symmetric. It isn't perfectly 2 individual cubes. And what this results in is 3 potential solutions for each pattern. So in this example here on the right, the scan, you can see it's just basically a mess of 3 different solutions. And if you look at that, here's some simulated patterns that Mark DeGraaf gave me at one point. And you can see there that the patterns are very, very similar, almost impossible to differentiate by eye for those 3 different orientations. So that's what we think of as pseudosymmetry. So you could think of this, instead of indexing as tetragonal, you could index it as cubic. You lose the tetragonality in your results, but you could still get some data with some usefulness. So the other example is a stretched cube, like I talked about for martensite. This example is for PZT. So you have a displacement of of the yellow atom there. This creates the dipole that leads to the piezoelectric properties, and it's slightly tetragonal. This is exaggerated. If you look then at the indexing, so here's two different orientations, A-axis orientation, C-axis orientation. You can see they're very similar. You can see the difference in this case, but it is slight. So that's another example. But there's also the example of centrosymmetry, and this is something we do tend to ignore quite a bit in EBSD, but it is there. So in principle, EBSD breaks Friedle's rule, which governs X-ray diffraction. And what that means is that in non-centrosymmetric crystals, we can differentiate one plane from its negative plane. So an HKL from H bar, K bar, L bar plane. So the EBSD patterns not only reflect the Laue group symmetry, but also are sensitive to point group. In standard indexing EBSD patterns using Huff transform for band detection, we essentially ignore the intensities of the bands. It's somewhat there because it affects which bands are found, but we really only use the location, the position of the bands in the patterns. And so this limits our indexing to be sensitive only to the Laue group symmetry. So to overcome this, we would have to look at intensity profiles. And some recent progress is starting to be made by those groups who focus on dynamic pattern simulation. The Imo Winkelmann and Gerrit Nolze have done some work together, and I'll show you an example, as well as Mark DeGraff's group at CNU have done some experiments here. So these are the, all the point groups, and just showing you which ones are centrosymmetric and which ones are non-centrosymmetric. So the amount of detail in the patterns that we see in direct electron detection has got us thinking more about this, and also what we can see in dynamic simulation, that maybe we can overcome this limitation. Here's an example from the paper by Imo Winkelmann and Gerrit Nolze. You see reference there, and in quartz you can think of a left hand and a right hand. And if you look really closely, if you look at just the large full view patterns, you really can't see any difference. But when you get into the details around one of the zone axes, you can see there is a subtle difference. And in fact, if you look at the very small, the blow-ups on that one zone axis, you can see there's basically the one on the left is a mirror image of the one on the right flipped along the vertical axis. And so those are the kind of intensities and functions we look at. And those are kind of beyond where we are today, but we're starting to look at these kind of features, just to get you thinking about this. The reflector list, I mentioned, you have the ability to optimize now using the dynamic pattern simulation to figure out which are the best reflectors. And we've done a paper on that recently, would point you to that is very helpful. It shows the utility of that. Also, the kinematic, if you want to recalculate those because maybe you've changed the atom position slightly, this is the location where you can do it. Like I said, we can do this optimization. There's some nice tools for figuring out which are the best bands to focus on for indexing in the conventional manner. And then I mentioned we have experimental patterns. We also have the calibration, the pattern center calibrations included with those, so that you can hit that index button and then it brings it up in OIM Analysis in the re-indexer, and you can play around and do some indexing of that pattern to better understand it. And then I mentioned OIM Matrix and the master pattern. So we have the ability to build and simulate and use all that like I've talked about in the previous webinar. Just as an example, this is the build function. So you have to have loaded all the other phase information, in particular the atom positions, and then you can generate a master pattern. And then you can also do simulations. And so this is just an example. This is a kinematic simulation and a dynamic simulation. And so you can compare those and just helps better understand what you're working with. So switching gears, I want to talk now about templates and reporting. And this is a really big change from what we had before. I know there were a few people who used some of the features we had before for building reports, but we've improved that a lot, and I hope this makes it much easier to use and more kind of more universal in a sense. So, the idea is that you have data coming in there on the left, and then in the middle, you use a template to crank out a set of analyses, and then those analyses, you can crank that further and put those into a report format. So the idea now is it's really based on templates, which makes this, we use that powerful capability that we already have in OIM analysis and use that to build reports automatically. So the idea here is you build a template that has a whole set of analyses, you apply that to a data set, and then out comes a report. So the first step is you use OIM Analysis to analyze your base sample, to select the appropriate maps, charts, plots, whatever it is you think might be important for analyzing your materials. And then you save that into a template. And you export that template, save it somewhere useful you can remember. And then you create a report form for that template. So you load the template in, it has all kinds of features, and then you take those features, those components, and you put them where you want in a document. And you can also load various information like a header file. So if you want to use your company's or institution's logo, you can put that up at the top or wherever you want it. And you can also enter some text. So then you just use that report form, and once you have that, you really only need that once, and then you can create a Word file. And this can be used both from Apex as well as from OIM Analysis. So you can use it on a single scan, or you can apply it to a whole set of scans quickly and get a report out. You can even do this from the command line. So you could use the command line to launch OIM. Basically, the idea is you launch OIM Analysis, you give it the file name, you use the keyword report first, and then the file name, in this case an OSC file, and then the report form. And it knows, it has a template associated with it, so it knows how to build that report. And that brings up the command line interface. Oops, I'm misspelling there. And it has some, basically you can use it to do kind of a scripting type approach using OIM Analysis. And I think this will be handy for those who maybe want to, build an automated system. So at the simplest level, you can just use it to launch OIM Analysis with a given data set. So in this case, you see, you just type in, and you use the Windows command prompt. And you have to first move your command prompt so that it's located within the bin directory for OIM Analysis. Otherwise, you have to put in a path name for it. Anyway, once you've done that, then you can just type OIMA, OIMA, and then the file name as you see there. And you have to put it in the parentheses, otherwise the spaces will mess things up. So that will just launch and load that data set, myscan.osc, and you're ready then to start analyzing. Now, you could apply a template. So in this case, you type in OIMA and then auto, the data set name, then the template name, and its full path name. And that then will open it and apply the template. You can also add some more functionality by adding the keywords +clean or +GE to the command right after auto. +clean will do a level 3 neighbor orientation correlation cleanup, followed by CI standardization. And +GE will cause it to export grain data created using the options in the last. So it will use the options used the last time you used the grain export dialog. So it doesn't have the capability of resetting all those options. So whatever you did last, it will remember and apply that for the export. You can do a batch recipe. So you can, in this case, you can load a file or you can load a folder of files. In my example here, it's a folder. So you say OIMA, use the keyword batch, the folder there in blue, and then in green, the recipe. So I've created a recipe, and that's off the batch processor. So off the batch processor, you can build it in OIM Analysis and then save that recipe as a text file, and it will use that and apply it to the data. So that allows you to do some really automated analysis. Remember, the batch recipe can include templates and things. So you have all that template capability, plus all the cleanups, maybe cropping, all kinds of things like that that you can apply and really get a lot of data out. We've also expanded it to include the reindexer. So once again, use OIMA, the rescan keyword, and then the file name. In this case, it's a HDF5 file that contains patterns, and then a file to apply a batch recipe. So you can rescan it and then apply a batch recipe to it after that. Oh, I'm sorry, I've got that wrong. So that's a mistake in my slide here, I'm sorry. It's not apply a batch recipe. That part there in the orange red there, that's a file to contain some data after the rescan. So it will rescan the data and save it, but then it will also tell you what the average IQ, confidence index, and fit is in that small little text file. So that covers all the new features for the command prompt level. Hopefully that's helpful to those of you who are looking to do more automation to apply to maybe some of you other functionality. One fun thing that we got involved with is the idea of perceptually uniform color map. So if you look at the top example there, let me jump ahead here. We have our nice little rainbow plots or color scales that we use. And you'll notice that some colors actually kind of disappear when you look at small variations. So at the top of these, I've done a 10% variation in the value used for the color scale. And you'll notice in the top row for the thermal one, the red really disappears, black disappears, the yellow disappears. In the other one, you see that the green really disappears and the red disappears. And there's also some kind of false boundaries that are too strong. It's more obvious in the rainbow one because you'll see from cyan to green, there's almost an artificial boundary there. From green to yellow, there's a pretty strong boundary. So our color maps aren't perfect. And so we've looked into this idea of perceptually uniform color maps. If you look at Peter Kovesi's website, you'll see that I have listed there. You'll see a lot of examples of this. It's kind of a fun website to look at. But there's been some work on this. There was some nice work done by Ralph Hilscher for MTEX that looked into improving it for color mapping. And Will Lente and Mark also worked on a paper on the same idea. And so we've taken some of those ideas, particularly from Will's codes, and incorporated them in to see what we could do. So there's a lot of different color scales now that you can use in these perceptually uniform color maps, so you have a lot to work with. And these are just some more. He has, Peter Kovesi's website has these different types of color maps. In this case, he calls it a diverging one, and then we have different rainbows. And these isoluminant ones are really designed not to show hardly any variation. You'll see at the top of that color scale, there's hardly any variation at all. And there's certain cases where that can be useful. And then we also have some that are designed to help those who are colorblind to hopefully improve some of the color maps for them. And now we've also applied this to the IPF maps. And you can see then the regular ones we have are on the left, and then the new versions are on the right. So you'll see on the color triangle there, it's a little smoother, and the symmetry's applied a little better for in the case where you have the cubic with the inversion symmetry. And you can see that for all of these different applications. So we've improved the color mapping. Just a word to the wise, to go to this perceptually uniform color mapping, we've had to go, and to improve the symmetry, we've had to add in black and white. Before, we basically just went with with red, green, and blue as our primary colors and then mixes of those, but we can't get the full symmetry for the lower symmetries. You'll see there in the tetragonal case. We also include black and white. And that's great and works well, except for the case where then you're trying to overlap it over a grayscale image. And then you lose that contrast. You can still see it, but you're mixing grays and whites a little bit, so it gets a little confusing. So just be forewarned about that. Just more examples for the lower symmetries. So here's just an example. On the left is our regular color triangle. On the right is the perceptually uniform. And you can see there are some differences. It's not dramatic, but the color variations tend to be a little bit more consistent. Here's an example then where we pull in the black and white, so we have a different way of dealing with the symmetries within the triangles, which is a bit improved, but you can then see the differences there. So there are some cases, you'll notice in that kind of on the red-orange grain, you see the color variations a little better with the perceptually uniform color map for that color. But then there's others where it's maybe not as clear, especially that really dark one, as you might expect in the middle of the screen there. But something to experiment with that I've had myself had some fun with. Now, in the previous version of software, we had NPAR, which is really useful for improving pattern quality. So this is the neighborhood pattern averaging and reindexing, NPAR. But now we've added a new variation of that. We call it non-local pattern averaging and reindexing, NLPAR. So if you remember NPAR, you take a pattern and all of its neighbors, and you come up with a nice, smoothed, improved pattern, as you might see in that example schematically there. And then you reindex it. So just as an example, here's an example for duplex steel with artificial noise. So we've got patterns at every point, and we're going to add Gaussian noise to them, fractions between 0 and 1. And compare it to the scan without any noise, our original scan. So here's our original scan on the left. And once we get to lots and lots of noise, see the variation on the right. So we add, what we do is, with the noise here, is just apply Gaussian out to 10%. And so what 100% noise means is we've applied this Gaussian to every single pixel in the pattern. And that results in a noisy result. Now we can apply NPAR and improve that, but one of the problems with that approach is if you have very small features, they get smoothed out because you basically smooth the image. So an individual pixel will lose its uniqueness because we smeared in the patterns from the neighboring pixels. We've averaged those in. So, for example, these small twins tend to get lost in this example using NPAR. So we wanted to use the idea, we did some studies when we first did NPAR about ignoring patterns if they're too different, and that gave us some improvement. As you can see here, we called it selective NPAR, and that worked okay, but we weren't totally happy with it, so we left it out. So in a work done by folks at Naval Research Lab, I thought I had the reference here, I'm sorry. I missed that. This is from the paper, and it's this is the math from it, and the key is that we're going to basically include larger kernels in our averaging, but we're going to weight them according to their difference from the pattern at the center. So here's an example of a pattern at the center of a kernel, and there's the raw pattern, and we can do our NPAR and everything. It works great. But we could also go out to third nearest neighbors and use them. If we do that, then you can see our patterns get somewhat mixed because we are at a boundary and we've got patterns from 2 different grains, so we have an overlap mixed pattern. But if we do NLPAR and weight those, then you can see then that the weighting is reflected in the graphic here by the brightness. So the pattern at the center is very bright. Notice there's another pattern quite similar, quite far away, a third nearest neighbor, which was a little surprising as we do this, but you can see that. And then you can see, so if we did NPAR, we get that mixed pattern. If we do NLPAR and weight them, then we get a nice, clear, clean pattern for that, all those patterns averaged together. So here's the conventional, and then just using it as usual. If we do NPAR, we get a smearing of those details. If we use NLPAR, we get just as good as indexing, but we still retain the fine structure, which is great. This one, you'll notice that K equals 5. That's so plus or minus 5 nearest neighbors, or fifth nearest neighbors, I should say. So that's great for a regular nice scan, but how does it work with really noisy data? You can see it really does a great job. Here's an example where we've added noise, and you can see the resulting NLPAR pattern is very clear and sharp and easy to index. And so here's a whole set of results. We've also compared it against the dictionary results. So like I said, it retains the fine structure, but it allows us to do larger kernels, which is great because it gives us more averaging. But because of all this, it is quite a bit slower. But if you really need, if you have a very difficult sample, it really can provide an excellent result, as you can see here, for our very noisy data. NPAR gave us some pretty nice data, but we lose the structure. We go to NLPAR, we get really nice results, even at that rivaling the dictionary approach. So the conclusion on that is that NPAR works well. Its best performance is when the noise is due to things like camera gain as opposed to inherent challenges in the sample. That's something we've learned. So it's an ideal in cases where the speed is a critical issue, so you're really going to a high gain, low exposure condition for speed. Cases such as in situ, 3D serial sectioning, or maybe you have drift correction or beam sensitive situations. The NLPAR is even more useful. It gives really good indexing success rates while retaining the fine structure, but it is considerably slower. So in cases like where you really want speed, then you'll have to, you can't do it on the fly. These aren't on the fly techniques anyway. You'll want to collect your data quickly and then use NLPAR in post-processing there. In fact, you might, to speed it up, you might not even index your patterns when you know it's going to be a problem. So that pretty much concludes the results that I wanted to show today and the new features. I hope that is useful to everyone, and I hope that you'll tune in for other webinars or other blogs. I see there's a couple of questions, and we definitely have time to go through some of those. There's a question about biological materials and perform in this case EDX on them, but I would assume EBSD. It's difficult. There have been a few results. The key is that we have found to do that is to get your system all focused in one area, and then when you want to do your EBSD, to not even worry about maybe indexing. You just got to get some patterns to get started. So go ahead and run that. Get your thing set up, move to a new area, and then collect patterns as quickly as possible. That's kind of suggestion. You might want to check with your applications engineer and can give you more information specific to your sample. The perceptually uniform color is not the default color spatial analysis. We continue to use the ones that you're familiar with, and hopefully you can switch to the others if you'd like. Obviously, you can build templates and things that use those, and so that should work great for you. I feel bad that I left off the meant to include the slide from our paper, and I'll try to put that in a future release where it's pretty easy to find. NLPAR is a lot slower. That is in the paper. Sorry, I didn't include that. I thought I had the paper handy, but I don't. So I'll have to send you that information. And the NLPAR method, there's a question on how do you define K. and what are the parameters which should be taken into account to determine it. It really is going to have to be an iterative experimental thing. Obviously, the smaller k is, the faster it will go, so I would start small and then maybe go and see if, so maybe start with 3, go to 4 and 5 after that, see if it improves it. There will be a point where it will drop off. I mean, you can use a very large one, but you will have to be patient. It does take some time. Let's see. So in terms of dictionary indexing and NLPAR, I think it is a good idea to combine the two. And that is something that we haven't done yet, but we'll be working on to make that possible. Actually, no, it is possible. But you will have to be prepared. You will have to have some time. It's the kind of thing you might want to run over a weekend. So hopefully that's all helpful. In terms of other questions, thanks to those who have said hello, friends out in the field. In this time of COVID, it's nice to talk to people as we're all been in isolation, so it's nice to hear from you and appreciate the kind words. The rest of the questions I think we'll answer offline, and then we'll call it a day today and hopefully enjoy the rest of your day. Thank you. Turn the time